Hello everyone, I'm Elleanna Viere, and my project this summer was reconstructing the historical ice cover of the Great Lakes from 1898 to 2022 with my mentors Dr. David Cannon and Dr. Wang. My main research question this summer was seeing if ice cover could be reconstructed, hindcasted, or past predicted using air temperature data. First, a little bit about me. I grew up in central Minnesota, and I now go to school at Northland College. I'm a climate science major and graduating next May. I'd also like to say thank you to the CIGLR Summer Fellows Program and the fellows and interns here this summer, along with the CIGLR and GLERL staff for a fun summer, and those that had input with this project. First, a little overview of how this presentation is organized. I'm going to first start with some background on the ice cover and air temperature data, and then the temperature variables that came from that, and then onto the model and the hindcast that was made, and the climate indices that could be correlated with Great Lakes ice cover. And just to preface this, I'm only mainly showing Lake Superior data, but this was all done for all 5 of the Great Lakes. So first, we have ice cover records going back 50 or 60 years, depending on if you're looking at average or maximum ice cover. First, there is annual average ice cover, or AAIC. This one is from 1973 to 2022, shown in a percentage in this graph over here. We can see that there is lower years of frequency for the ice cover compared to last year's, and then there is annual maximum ice cover, or AMIC, from 1963 to 2023. With ice cover only going back this far, it's hard to tell what could happen in the future, especially with increasing temperatures, so decreasing ice cover. And it's important to know this for the Great Lakes region, which relies on ice cover economically, ecologically, and culturally. But there is air temperature data going back to 1897. These 24 stations around the Great Lakes have been collecting this data from 1897 to 2023. We used the daily average temperatures to find 3 temperature variables, which I will explain later in the slides. Visually representing this data is for Lake Superior yearly average of the daily average temperatures. From 1897 to 2023, we can see a pattern of initially decreasing, increasing, and then so on until we get to here where it is mainly increasing temperatures around the lake. And then if we were to zoom in on a certain year, we would see this from May 1st to April 30th with increasing summer temperatures and then decreasing down for the fall and winter and increasing back up in the spring. And this is the time frame defining the winter season that we would take our data from for a given year. So for the 3 temperature variables that there were, the first one is the summer heat content of the lake. This is the accumulated degrees in Celsius throughout this time. So this is like, let's say there's 5 degrees above Celsius one day and 10 degrees another day. You add those together and it accumulates to 15. And if it's another 5 degrees the next day, you would get 20 degrees. At the end of the season, at September 30th, the max amount will be taken and used in our model. The next day is the thawing degree days, or TDD. This is from October 1st through April 30th, and same as the summer heat, it would accumulate during this whole entire time, but only for the days above freezing. So if it was 5 days again and 10 days the next, it would be 15. But let's say it was -5 degrees the next day, it would subtract from that 15 and go down to 10 degrees for the accumulation of that given day. But this cannot go negative, so the lowest it can go is 0 degrees. And whatever the max value is at the end of during this whole period is what we used in our model. And then lastly, there is freezing degree days through the same period as 9 degree days. It's just the opposite. It is the positive days below freezing for this given time period. So again, this cannot go negative. So the first day that it would accumulate, it would be that one for this time, for this year. And then whenever it would go above freezing, it would subtract from that total. So if it was 10 degrees accumulated below freezing, and if it went 5 degrees above, it would subtract from that to be 5 degrees freezing degree accumulated by that time. For all of these variables, they cannot go negative. So the lowest that can go again is 0. And we use the accumulation max value for this given year in the model, and they reset after each year. These were then used in our model. First, we began with a linear regression model, but that went negative, and ice cover cannot go negative, so we couldn't use that one. So we used the beta model, which is bounded from 0 to 1. So ice cover, since it's a percentage, it works perfect for this. Different variable combinations were put into this model to find that max freezing degree day, max thawing degree day, and summer heat was the best one. We also did this individually for each variable, and it was also found that max freezing degree days by itself was also comparable to this. In this equation, we can see that this is how the beta model works with each year given. This works for average ice cover and maximum ice cover. For this part right here, this is the xbit or logit function, where it keeps the data bounded and transformed between 0 and 1. And then the x part, the exponent, is right here with the coefficients and intercepts changing for each model and for the lake. And then you times it by 100 again to get it to a percentage. The superior annual average ice cover equation is an example of this, with the coefficients and intercepts changed. The model was then trained between the period of 1973 to 2022, and we can see this in that graph, with the green line being the average ice cover shown previously in this presentation, and the black line being the predicted from the model. And they're very close, with a few years being off, but with our values being between 0.83 and 0.94 for average ice cover, it is fairly good for an ice model. And then for maximum ice cover, we got our values between 0.69 and 0.86. So it didn't do as good as predicting the maximum ice cover, but still really good. And then if we were to look at the entire hindcast, we would see this. So same as the last one, the black line is the values hindcasted by the beta model, and the green line is the observed values of average ice cover. This part of the graph is the same part as shown on the last slide, but now we have the hindcasted data in there. We can see the trends in here with a decreasing of ice cover, increasing, and then decreasing again. Also, we can see that there are more frequent years of lower ice cover, and it has happened before in the 20s and 30s, but now it is happening more frequently with the lower temperatures or higher temperatures that we are getting in lower ice cover. We can also tell that since this is the only data of ice cover that we had in the green before, there would be a more like decline in the ice that we've seen if we were to draw a best fit line. But since we have this data of what the ice cover probably looked like beforehand, since the ice cover is at a lower now, it would be less of a decrease compared to now. It's just a different way of looking at what ice cover was, how is it is decreasing right now. And here are the 4 other lakes hindcast too. So same as the other one, they have the black line being as the beta model predicted values, and the green line as the observed annual ice cover for that lake. And we can see, as same as the superior, we have the trends of decreasing, increasing, and then decreasing ice again. It's a little harder to see in Ontario as it's kind of all just decreasing, but you can slightly see this increase again right here. And we can also tell that there are, in the 1920s and 30s, that there was this lower ice cover, but it is happening more frequently here in this since the 2000s and 1990s. So then we used these 4 climate indices to compare them to the hindcast. So the climate indices that we used were the Atlantic Multidecadal Oscillation, or AMO, the Pacific Decadal Oscillation, PDO, North Atlantic Oscillation, NAO, and El Nino Southern Oscillation, ENSO. And these were all put in that same beta model that we used to hindcast the ice cover, but instead of the temperature variables, we used the climate indices. And they were all put in there individually and all once together. And with R² and root square mean errors, we found that the model with all 4 of them together worked best, but with comparing all of them individually, the AMO also worked well compared to the other 3, and it was also comparable to the one with all 4 of them together. And we can see this in this graph. So the black line is the hindcasted data from that beta model using the temperature variables, and the blue line is the predicted values from the indices all together. So we can see that the model with the indices did not get the variability that the temperature is able to get with the temperature or with the ice cover, but it is able to get those cycles that we were seeing before of the decreasing, increasing, and decreasing again. And in conclusion, that the daily average air temperatures of the Great Lakes can accurately describe the ice cover from 1898 to 2022 using the freezing degree day, max thawing degree day, and summer heat variables. And then climate indices don't fully explain the variability in ice cover as well the temperatures do, but they do describe those cycles that we saw. And lastly, if temperatures do continue to rise, then ice cover will likely decrease, especially of those if we don't get those freezing degree days. And thank you.
All right, great job, Elleanna. We have some questions for Elleanna.
Great presentation, Elleanna. I had a question since the temperature was able to hindcast so well, I was wondering why did you guys also look at climate indices on top of that?
So we want to see if the climate indices were impacting like the weather patterns and the temperatures on the Great Lakes, since they do include like sea surface anomalies and stuff like that. So with that, it helped explain how the cycles of the ice cover were going, rather than the temperature cycles that were shorter and more frequent. This was explaining how the ice cover models were going.
Great.
Great talk, thank you. I just wondered if there's any like theories or indication of it hindcasts so well, but there are those years that have like that big difference. Is there any like theories why those singular years are sort of outliers?
It could be from the indices, but I don't know for sure. That's just my guess. It might be from the indices, it might be from something else. Maybe wind. There's a lot of wind that year. I don't know. But that's a good question.
Elleanna, I've got a question as well. So if the last slide you were on, oh, no. I think it was this one. So in some of them the hindcast shows some pretty wide range of variability in like the 1920s and 30s. Is that reflected in the air? Is that reflecting what you would see in the air temperature data? Was there just really widely varying air temperature differences during those years?
From what I remember, if we go back to this slide, the yearly average, we can see that there is lots of variability in the 1920s and 1930s.
Yeah, great, thanks.
Great talk. It's a really interesting tool model to look in the past. I'd be curious to see, how you can use it to try and predict the future using, projected air temperature stuff. You showed a map, I think, early on that showed like where the stations were located. Cool. Okay, so there's multiple stations per lake. So all of those stations have data going way back in time.
Yeah. All of these stations, or they have like really close neighboring stations. If like it was like data wasn't good for a week or so, they would use that to average it out. So they were fairly similar.
Okay. I was just curious, was there much, I guess, sensitivity in your model to which stations were selected? Or I guess the first question would be like, was there a lot of variability from one station to the next? Or did they all sort of agree through time?
All of these stations data were like averaged over for the entire lake. So it wasn't just one station that was used, it was all of them averaged into one value for the whole entire lake.
Okay, thanks.
Hello, great talk. Thanks for sharing that with us. You partly answered this already. I'd really like to hear your thoughts on the assumptions that go into that approach that you showed, right? With the kind of using this temperature, you're kind of using it as a proxy for the heat flux, right? Is kind of the idea, I think. So could you talk, you said winds already. Do you have a sense of some of the assumptions that went into there? And are there opportunities for refining the method that are in those assumptions? You know, could they be revisited, for example?
Yeah, so water has like a high heat content and it can store heat longer. So that's why the summer heat variable got added to that. But we found like the R value for that. And in the coefficients, it wasn't like a main component to the ice cover versus like freezing degree days and thawing degree days. Because again, with like freezing degree days, you're not going to get ice if it doesn't go below 0. So that's why it was also a main component. Like if the model with just freezing degree days was also comparable to just this, and along with thawing degree days, if you have those together without summer heat, that was also comparable. But yeah, does that answer your question? Okay.
Thank you.
Kind of along those lines, did you look at the residuals from your model fit to get some sense of whether or not that relationship might be changing over time?
Are you talking about like what square mean values?
Well, it's related to that. It's the deviation between your model predictions and your observations. If those were stable through time, it would suggest that the model you developed was capturing things pretty well. If you saw a pattern in the residuals, it might suggest that relationship was changing over time. I don't know if you did something like that or not.
I don't believe we did. I don't think we did, but that'd be a good thing to do in the future to see if that has
The graph looks quite good, but you can't always tell from that. It'd just be interesting to see if something shows up.
Yeah, thank you.
Thanks, Greg. Okay, do we have any further questions for Elleanna? Oh, sure.
I just wanted to first comment that I think there are a lot of questions because you had such a good slideshow that everybody wants to engage with it and comment on it. So I just want to congratulate you on that. And I also wanted to ask, in the lake-wide trends, it seems like you said there's a decrease in ice cover, then increase, then decrease, right?
Yes.
And so I was wondering, what is the explanation of did you see an explanation for that initial decrease in ice cover?
Are you talking about the one happening in the early 19s or like now?
I believe you
Or just
spoke about like the 20s and 30s.
Okay. Oh, like those the variability?
Yeah.
Yeah. So I think that was mainly due to like higher temperatures happening. I don't know why, but if we go back again to this graph, so we have like the higher temperatures and the lower temperatures, but we don't fully know why. At least I don't. Possibly because of indices. I don't know. Good exploration for something in the future.
Yeah, great job. Thank you. I have a question that I think might be related to James a little bit. So when James asked about how there were the different temperature stations along the lakes and you averaged them together to get total lake coverage, I'm wondering if you just thought, like, while you were going through this, if you thought about, if there were, like if you had split the lake up by different areas, in Lake Michigan, you have Green Bay, which I'm assuming is going to have different, maybe like ice dynamics than like the rest of Lake Michigan. I don't know if you noticed if like some of the like daily temperature stations were like higher than the rest of the lakes, or just have you thought about if you were able to like split up these models to look at like different sections of the lake?
Yeah, so like originally going through this, I was wondering if we would like doing different basins of it. And in one of the papers, it does mention doing different basins. And like the earlier like 1980s papers, but we just decided to go with an all average to make the model simpler. But yeah, thank you.
Okay. Any one last question? Elleanna? Okay. All right. Thank you so much. Elleanna.